Hello everyone. Welcome to the next lecture on the numerical linear algebra. Today I will explain you the concept of the orthonormal basis. Myself Dr. Harish Garg. You can follow and subscribe my YouTube channel where you can find the playlist of the numerical linear algebra. The last lecture was on the orthogonal and the orthonormal vectors, and later on you can see the Gram-Smith process, power method for the eigenvalues, and many more lecture in this playlist. You can follow and subscribe it for more updated videos. Now, what is the concept of the orthogonal basis and what is the concept of the orthonormal basis? So we will see the concept of both orthonormal and orthogonal basis in this lecture. First of all, if I quickly recall you the concept of the orthogonal and the orthonormal vectors, if you have the n vectors v1, v2, vn, then the set of the vector is said to be the orthogonal whenever vi dot vj is my 0 for all I is not equal to j. That means if you take the dot product of the v1 and v2, it must be 0. Dot product of the v2 and v3 will be 0. Dot product of the v1 and v3 will be 0, and so on. On the other hand, the vectors are said to be the orthonormal if vi dot vj will be 0 for all I is not equal to j, and the second property is the norm of each of the vector, the length of the each vector must be 1. Then you can say the vectors are said to be orthonormal. Now, based on the orthonormal and the orthogonal set, we can define the concept of the orthogonal basis. Fine. A set of the vector is said to be the orthogonal basis if, number one, firstly you need to prove that the set v1, v2 and vn, that is the vectors, are orthogonal. Fine. And second is the vectors v1, v2 and vn forms a basis. This form a basis. And we already know how you can prove the orthogonal, or called as a pairwise orthogonal. That means if you prove that vi dot vj is my 0, and how you can prove as a basis? For the basis you need to prove that they are my linearly independent and the elements span the given dimension set, the span of the V. If you prove these two elements, then you can say this is a basis and the orthogonal elements. So once you can prove the A and B, then you can say the vectors is said to be orthogonal basis. On the other hand, how you can prove that the set of the vectors are orthonormal? Instead of proving that they are orthogonal, you have to prove that they are the orthonormal. How you can prove the orthonormal? That means vi and vj must be 0 and the norm of the each element must be 1. That is the property of the first part. While for the second part, again you have to prove that they are Li and they are span. One more interesting property is that if you already prove that the set of the vectors are orthogonal, that implies if you prove that v1, v2 and vn, if you prove that these sets are my orthogonal, then it automatically implies that the elements or the vectors v1, v2 and vn are my Li. Fine. Because in order to prove that it's a basis, you need to prove that it's a Li. Fine. But if you prove that the set of the vectors are my orthogonal, then there is no need to prove they are Li. They are automatically Li. That means every orthogonal vectors are linearly independent. Fine. An orthogonal set of the non-zero vector are always linearly independent. Now, so again I recall you what is the meaning of the orthogonals. That means the dot product between the elements or the vectors is my 0. For example, if I consider the set collection of S from the R4, so if I use this element is my V1, this element is V2, this element is V3, then what is the V1 dot V2? If you take the dot product, how you can take the dot product? The first element multiply with the first element, second element multiply with the second element, third element with the third, fourth element with the fourth, that is a 0. v1 dot v3, first element with the first element, second element with the second, third element with the third, fourth element with the fourth. Similarly, v2 dot v3, first element with the first element 0, second element with the second element, third element, fourth element. Fine. Now what does it means? If all these elements are my 0, that means v1, v2 and v3 are orthogonal vectors. Fine. So these are my orthogonal vectors. Now you can find the norm. What is the norm of the v1? It is 1 square plus 0 square plus 0 square plus 0 square. So that comes to be 1. Similarly, norm of the v2 is again 1. Norm of v3 is again 1. What does it implies? That means the set of the vectors are my orthonormal. So therefore, the given set S is my orthonormal. Fine. Now, one thing you have to prove. The second is you have to prove that whether it's a basis or not. Fine. Whether it's a basis or not. Now, because you can simply say because the elements or the set or the vectors v1, v2, v3 are my orthogonal. Fine. So therefore, you can say the vectors v1, v2, v3 are my Li. Fine. Now you have to prove that it's a span, whether it forms a span or not. Now clearly say what is the dimension of the R4. Dimension of the R4 is 4. And what is the dimension of the S? Because they are Li, so dimension is my 3. And clearly say both are not equal. And once they are not equal, that means they are not basis. Fine. So once they are not basis, you can say the given set S is not orthonormal basis. Fine. So it is not orthonormal basis. Look at the second example. If I choose the set S, if I consider this is my V1, V2, V3, V4, check whether they are orthogonal or orthonormal. What is the V1 dot V2? 1 plus 0 plus 0 plus 0, which is my non-zero. So what does it mean? That means the set which consists of the V1, V2, V3 and V4 are not orthogonal. Fine. And once they are not orthogonal, that means they are not orthonormal. Fine. And once they are not orthonormal, that means the set S is not orthonormal basis. Is not orthonormal basis. Or the set is not orthogonal basis. Why? Because the first property is not satisfied. Whether now is, can you say is a basis? First of all, you can see what is the dimension of the S. Dimension of the S is 4, and also these are the elements of the R4, which is my R4. Fine. And whether it's a basis or not, you can check whether they are Li or not. And how you can check about the Li? Because they are not orthogonal, it doesn't imply that they are not Li. How you can prove the Li? I can multiply with the first element with the alpha 1, second element with the alpha 2, fine, third element with the alpha 3, and the fourth element with the alpha 4. And my target is to check the values of the alpha i's. So now you can see if you equate the first component, alpha 1 plus alpha 2 plus alpha 3 plus alpha 4 is 0. For the second component, alpha 2 plus alpha 3 plus alpha 4 is 0. Then alpha 3 plus alpha 4 is 0. And the last one is alpha 4, 0. Clearly say from here you can see alpha 4 is 0. If you substitute the value, alpha 3 will be 0. If you substitute the second equation, alpha 1 will be 0, and it is alpha whole here. So therefore, the given set is my Li. Yes, it is a Li as well as a span also. Therefore, this S form a basis. This form a basis. Why? Because S is Li and the dimensions are same, but S is not orthonormal or orthogonal basis because the dot product between the any two elements is my non-zero. Okay, look at this another one. Check whether the V1, V2, V3 are orthonormal bases. So that means your target is to check whether the given set or the given vectors are my orthogonal, and second is your target is to check whether they form a span as well as the Li. That is your target is to check whether they are form a basis or not. Now let's start with the firstly how you can check about the orthogonal. So we can start with the v1 dot v2, then v1 dot v3 and v2 dot v3. So what is the v1 dot v2? If you substitute them, it's a minus of 2 plus 1 plus 1, which is my 0. v1 dot v3, 0 plus 1 minus 1, which is 0. And v2 and v3, this number is my 0 plus 1 minus 1, which is 0. So what does it implies? That means the given set of the vectors v1, v2, v3 are my orthogonal. Fine. Orthogonal set of the vectors. And once they are the orthogonal set of the vectors, you can say yes, they are my Li as well. Fine. The given set of the vectors are my orthogonal, therefore they are Li as well. Now, in order to prove that it's a basis, you need to prove that span and the Li. Fine. So Li we already seen because they are my orthogonal, so it's Li. How you can prove the span? So clearly say what is the dimension of the v1, v2, v3. If I consider S is my collection of v1, v2 and v3. Fine. Then the dimension of the S is 3, which is the same as the part of the R cube. These are the elements of the R3. Therefore, S form a basis. Fine. Now, S form a basis. S is orthogonal. That means the given set of the vectors are my orthogonal basis of the R cube. Now, the next result is if you taken any element of the subspace, then we can write as the linear combination of the orthogonal basis. That's a very, very important concept. That means if you consider any elements, say this is my vector space Rn, fine. If you taken as a v1, v2 and say vn, this is my set S. Suppose S is an orthogonal basis of the subspace W of the Rn. If you take any element of the Y, then you can write Y as the linear combinations of v1, v2 and vn. So my target is to find the values of the Ci's. In other words, you can say if you have the set of the orthogonal basis, what is the meaning of the orthogonal basis? That means the set form a basis as well as they are my orthogonal. Fine. Then for each element Y of the subspace, we can write as the linear combinations of the Vi. The proof is a very, very simple. What is given to you? It is given that the vectors v1, vn are my orthogonal. That means vi dot vj is my 0 for I is not equal to j. Now I can take any element y which is the part of the subspace, then we can write y is my c1 v1, c2 v2 and so on. If I write as equation number 1, then I can multiply equation number 1 with v1. Fine. So what will happen? It is y dot v1, which is c1 v1 plus c2 v2 plus up to cn vn dot product with the v1. Now if you open this bracket, c1 v1 dot v1 plus c2 v2 dot v1 plus, and the last is cn vn dot v1. Fine. this number will be C1 V1 dot V1, and by using this equation number star, Vi dot Vj is 0 for I is not equal to j. This number will be 0, this number will be 0. So hence, can you find the value of the C1? C1 will be y dot V1 divided by V1 dot V1. That's the value of the C1. Similarly, if instead of the V1, if you multiply with the V2, then I can find the value of the C2 is y dot V2 divided by V2 dot V2. Similarly, C3 will be y dot V3 divided by V3 dot V3, and so on. Clear? So therefore, for if, remember, if it is orthogonal, then only you can write as a linear combination, otherwise not. Fine. So look at the example. Express 374 as a linear combination of the orthogonal bases. What is the meaning of the orthogonal again? If you consider this is my V1, this is V2, this is V3, then clearly say what is a V1 dot V2? 1 minus 1 plus 0, that is a 0. V1 dot V3, 0 plus 0 plus 0, again 0. V2 dot V3, 0, 0 plus 0, again 0. That means yes, they are my orthogonal. Fine. And how you can prove that it's a basis? So clearly say once is orthogonal, that means they are my Li. Once is Li, clearly say that dimension of this vector is my 3, which is same as the dimension of the R cube. So yes, it form a basis. Therefore, it is orthogonal basis. Now, your target is, what is your target? Your target is to write 3, 7, 4 as a linear combination of given vectors. C1, 1, 1, 0, C3, 0, 0, 1. Fine. So I can use the same result as I mentioned you in this case. If you compare them, this number I can take as a y, this number I can take as a y v1, this number is v2, and find this number is my v3. Fine. Then we can write the c1, c2, c3 are my scalars such that the value of the c1 will be y dot v1 divided by v1 dot v1. c2 will be y dot v2 divided by v2 dot v2. Similarly, c3 will be here. Now, can you find the value of this number is my y? Fine. And this number is my v1. Can you find the dot product? This number is my 3, then minus 7, then plus 0 divided by v1 dot v1. This is my v1. You can find the v1 dot v1. That is a 1, like 1 minus 1 0. This is a v1 dot product with the v1. So that number is 1 into 1 is 1, minus 1 into minus 1 plus 1 plus 0. So the answer is minus 4 divided by 2, that is minus of 2. Similarly, for the second part, how you can find the C2? Y, this is the y and this is my V2. If you take the dot product, it is 3 plus 7 plus 0, and the V2 plus V2 is 1 plus 1 plus 0. That is a 10 over 2 is my 5. And for the last case, y dot V3, 0 plus 0 plus 4, 0 plus 0 plus 1. Answer is 4 over 1 is 4. Therefore, you can write as a linear combination is 3, 7, 4 is a linear C1. C1 is my minus of 2. C2 is my 5. Fine. And C3 will be my 4. Fine. So therefore, we can express 3, 7, 4 as the linear combinations of this element. You can check your answer in the examination as well. The first component is my 3. If you look at the first component, this is my minus of 2. This component is my plus 5. This component is my 0. And you can see the answer is 3 satisfied. Similarly, for the second component 7, this number will be my 2. This number is my 5. And that this third component is 0. Again 7 satisfied. Same for the third component 4 is a 0, 0 and 4 is the correct answer. Let V is the collection of all those matrix. What is M2? That is a collection of 2 cross 2 matrix. with the elements are my real, R is for the real, which are defined as the inner product, that is the element is A1, B11, that's the first element, second element and so on. Then let W the subspace of all those symmetric matrix, then find the component of the vector this with respect to the S1. If I consider this is my V1, this is V2, this is V3, and I consider this element is my Y, then your target is write the value of the Y with the respect of the linear combinations of V1, V2 and V3, and your purpose is to find the value of C1, C2 and C3. Fine. But before that, how you can write? If you write the value, if you write these linear combinations, but before that, you can only write if you prove that V1, V2, V3 are my orthogonal basis. Fine. And how you can prove the orthogonal? Firstly, you can prove that V1 dot V2 is 0 or not. Let's see. What is a V1 dot V2? This is my V1, this is V2, this is V3. So first element with the first element 2, second element with the second element -1, -1 into -1, 0 into 2 is 0. Answer is 0. V1 dot V3. Fine, because the elements definition is A1, A11, B11, A12, B12 and so on. 2 into 2 is 4, minus 1 into 2, minus of 2, minus 1 into, and 0 into 3 is 0. Similarly, V2 dot V3, 2 plus 2 plus 2 minus 6, which is 0. Therefore, the given set of the vectors are my orthogonal. Once they are orthogonal, that means they are Li also. Again, you can find the dimension of the S, you can find the dimension of the V as well. Fine. So clearly say they are my orthogonals as well as the basis. Now you can write as a linear combinations. What is the value of the C1? Y dot V1, V1 dot V1. So can you find the value of Y dot V1? This number is my Y. Fine. This is my V1. You can multiply them. It's a 0, minus minus plus 1, minus 1 into plus 1 and 0. And what is the V1 dot V1 is 4, because what is the V1 V1 minus 1 0. You can take the dot product with the V1 again. Fine. So 2 into 2 4, 1 minus 1 into minus 1, minus 1 into 1 and 0. So the answer is 2 over 6, which is 1 over 3. Similarly, you can find the value of the C2 as Y dot V2. This number is my 1 over 3. Similarly, you can find the other two numbers, and after the calculation you will get 2 over 7 minus 10 over 21. So therefore you can write the vector V, that is a Y, as a linear combinations of the other element. And you can also check your answers. Look at the first answer is 0. In this case it is 2 over 3. This case is my 2 over 7. Fine. And this number is my 20 over 21. If you take the LCM 21, it is 7 to the 14, 6 minus 20. You can see 20 minus 20 is 0. Left hand side satisfied. Similarly, you can side satisfied for the other three entries as well. Okay, consider the vector space P1. P1 is a collection of all those polynomial of degree less than equal to 1. That means collection of A plus Bx. Fine. With the inner product, integration from -1 to 1, P and Q. Check whether the vectors form a orthonormal or not. Fine. So that means your target is to prove the two things. Firstly, you need to prove that whether they are orthogonals, and second is whether they form a basis or not. Fine. So very simple again. Firstly, we will check whether they are orthogonal or not. That means there are only two vectors. Your target is to prove that P1 dot P2 by using the definition of the inner product. It is integration from -1 to 1 P1 into P2 of dx. So can you find the integration? What is the P1? 1 divided by root 2, and it is root 1.5. X is outside. I can take root 1.5 over 2 is outside. Integration of the x is x square by 2 from -1 to 1, and clearly say this number is 0.75 half minus half, which is 0. Therefore, the given set of the vectors or given set of the polynomials forms orthogonal. Fine. But since we need the orthonormal, so how you can prove the orthonormal? Instead of the orthogonal, your target is to prove the orthonormal. Fine. So for the orthonormal, you second thing you need to prove that norm of P must be 1, norm of the P2 must be 1. Fine. This is your target. Is it okay? So first case is this value I have obtained as a 0. Now how you can prove the norm? This is 1 to minus 1. This is P1 into P1. So that will be 1 to minus 1, 1 by root 2, 1 by root 2 into dx. 1 over 2 is outside. Integration of the x minus 1 to 1. So that will be 1 plus 1, 2. 2 over 2 is my 1. Similarly, this number will be P2 into P2. Fine. So if you integrate them, 1.5 will be outside. So 1 to minus 1. X into x is x square. Now if you integrate them, integration of the x square will be x cube by 3 from minus 1 to 1. So that number is 1.5. 1 over 3 minus minus plus 1. Fine. So that number will be 1.5 into 2 over 3. I can write as 1.5 is 3 by 2. So that is cancel, which is 1. So yes, they form a orthonormal set. Fine. Second thing you have to prove that it's a basis. Now since P1 and P2 are my orthogonal, fine. So that implies P1 and P2 are Li. Fine. Now second is you have to prove the dimension. What is the dimension of the P1 comma P2? They are the two elements. Fine. And what is the dimension of the given vector space? The given vector space is 2. Always remember, if you have the polynomial Pn, then the dimension of the Pn is my n plus 1. In this case, n is my 1. Fine. So 1 plus 1 is my 2. Now since both the dimensions are same, so yes, they are span and hence they form a basis. Once it's form a basis, your first part is over. Now the second part is you can write the q 1 plus x as a linear combination of the P1 and P2. Fine. Because we already proved that the P1 and P2 are my orthogonal. Fine. We already proved that P1 and P2 are orthogonal. So therefore, I can write the value of the C1 is y dot P1 divided by P1 dot P1, and C2 will be y dot P2 divided by P2 dot P2, where 1 plus y is my, where 1 plus x is called as the y. Here instead of the y they are called as a q, so I written this number is my q, so it is a q dot P1, q dot P2. Now can you find the value of the q and P1 by using the norm definition? Fine. It is a q into P1 divided by minus 1 to 1 P1 P1. Fine. So what is the q into P1? Q is my 1 plus x. P1 is my 1 by root 2. 1 by root 2 is outside. Integration from minus 1 to 1 of 1 plus x divided by 1 by 2 of dx. So if you take on the numerator, so 1 by root 2 is outside. It is a x plus x square by 2 from 1 to minus 1, and the denominator is my 1. If you substitute the value, that number will be 1 by root 2, 1 plus half. Then if you substitute minus 1, then it is, so half and half will be cancelled. It is 1 plus 1, 2 divided by root 2. So the answer of the C1 will be 2 by root 2, that is root 2. Fine. The value of the C1 is root 2. Similarly, we can find the value of the C2 minus 1 to 1. This is 1.5 x into 1 plus x. Denominator value will be 1 because they are orthonormal. We already proved that it's orthonormal. So 1.5 root is outside. Fine. If you solve them, it will be x plus x square. Integration from minus 1 to 1. That number is x square by 2 plus x cube by 3 from 1 to minus 1. Now if you substitute the value, 1.5 is outside. That value will be half plus 1 over 3 minus half minus minus plus 1 over 3. Half and half will be cancelled. 1.5 into 2 by 3. I can write as 1.5 is root 3 by 2 and into 2 by 3. Sorry, only 2 by 3. Fine. Fine. So how you can find that? So C2 is basically my root 2 divided by root 3. Fine. So C1 is there and C2 will be root 2 by 3. So I can substitute the value C1 and C2 in the given Q. We can write as a linear combination of these factors. Now these 6 questions are exercise for you. First of all, you can determine whether they are orthogonal basis over the C0. As I mentioned you, what is the C0? It's integration from A to B. Integration from A to B. If I taken as a 2 vectors, say f and g, then the answer is f into g of dx. So which of the following is my orthogonal basis? And for this case, if you taken as an inner product like a0, b1 and so on, check whether they are orthogonal basis for the given set of the polynomials. You can solve it problem and let me know in the comment box, have you understand this lecture very well or not? We will see the next lecture on the Gram-Smith process very soon. Till then, you can share this video with your friends. You can like and comment on this video. Happy learning always, students. Best wishes. Thank you very much.